Do you ever wonder why your car tire gets flat in the winter, or why steam comes out of a pressure cooker or pot, or why this egg can fit through this glass bottle? Well, I'll explain if you stay tuned. Gay-Lussac's law. Before we go into the experiments, let me provide you with some background information about Gay-Lussac's law. Gay-Lussac's law stems from the combined gas law. The combined gas law includes pressure, volume, and temperature. Although, in Gay-Lussac's law, volume is held constant, so we don't need it, and temperature and pressure have a direct relationship. The combined gas law equation is P1 V1 over T1, which is equal to P2 V2 over T2. The V1 and the V2 cancel out because they are constant, and we're left with the equation of P1 over T1 is equal to P2 over T2. When working with Gay-Lussac's law, the left side of the equation is usually known as the before, and the right side of the equation is usually known as the after of a reaction, meaning that the P1 and T1 are the before, and then the P2 and the T2 are the after. Looking at a graph for the combined gas law, you will see it's a straight line because pressure and temperature have a direct relationship. As pressure increases, temperature will increase, and as pressure decreases, temperature will decrease. When the pressure is increased, it allows for more collisions of the particles on the walls of the container. When the pressure is decreased, there are fewer collisions of the particles on the walls of the container. In the winter, the temperature outside decreases. In terms of Gay-Lussac's law, we know that this means the pressure must also decrease. So, in your tires in the winter, you might have to put some more air in them as the pressure decreases and the temperature decreases as the seasons change. On the other hand, inflated tires may burst in the summer because they're at a very high pressure and a high temperature, and at a certain point the tires will fracture or burst. Now let's look at pressure cookers in terms of Gay-Lussac's law. Displayed is a pot, which will show us a much clearer example than the slight changes made to a pressure cooker. In a pressure cooker, the volume is held constant, just like in Gay-Lussac's law, while the cooker is heated and the water inside the cooker vaporizes, producing steam. This gives us our direct relationship between temperature and pressure. To avoid rupture of the pressure cooker, steam is released periodically to maintain the necessary pressure for cooking. After a fixed amount of gas increases with temperature and the pressure release valve were to malfunction, it may unfortunately cause the pressure cooker to rupture. Now let's take a look at how this egg can fit into the glass bottle. First, I got my supplies: a hard-boiled egg, a glass bottle that won't let the egg fit in, paper, and a lighter. Putting an egg on top of the bottle won't allow the egg to enter the glass bottle, as the pressure inside and outside the bottle are the same, and the gravity is not strong enough to push the egg into the bottle. So I put a lit piece of paper inside the bottle and put the egg over the bottle. The heat from the paper heat up the molecules inside the bottle, increasing temperature and pressure as a result of Gay-Lussac's law. The increase in pressure forces the molecules inside the bottle to push against the wall in an attempt to increase volume, but pushes the egg slightly up and down, causing it to jump, releasing some air to rush out from the bottle and causing the flame to extinguish. The temperature begins to go down as a result of the flame extinguishing, and so does the pressure and volume as a result of the combined gas law. As there's less air pressure in the bottle rather than outside of the bottle, the pressure drops lower, and the outside pressure forces the egg into the glass bottle. Once the egg is in the bottle, the pressure will equalize so that the pressure inside and outside of the container is equal. The exact opposite is done when removing the egg, not shown here. Now let's go look at some practice problems. The temp of a Heinz ketchup container inside of the fridge is 277.4 Kelvin with a pressure of 200 kilopascals. The same container is now on the dining room table with a temperature of 283 Kelvin. What's the pressure of the Heinz container on the dining room table? If you want to try these problems on your own, please pause the video so you don't get the answer from me walking you through the steps. For starters, I set up my equation. P1 times V1 over T1 equals P2 V2 over T2. I know this is Gay-Lussac's law because this is dealing with temperature and pressure. It's the only things in the question, and there's no volume. Volume remains constant, so I can cancel it out, leaving me with P1 over T1 equals P2 over T2. My P1 is going to be the first pressure, which is 200 kPa, over K, which is 277.4 Kelvin. And then that is going to be equal to X because we don't have the second pressure, which is what we're trying to find, over 283 Kelvin. I multiply the equation by 283 on both sides to get X secluded on one side. So I have 283 over 1 times 200 over 277.4 equals x. I calculate it and get 204.043. To add my units, my answer is 204.043 kilopascals. Question 2. A container of gas has a pressure of 240 kilopascals at 20 degrees Celsius. That container changes in temperature to 321 degrees Kelvin. What is the new pressure? Now I need to use Gay-Lussac's law because I'm only dealing with temperature and pressure, as the question does not ask about volume, and volume will remain constant. My new equation is P1 over T1 equals P2 over V2. I see that my 20 degrees Celsius is different than my 321 degrees Kelvin because of the units. So I must convert my 20 degrees Celsius to Kelvin by adding 20 plus 273 equals 293. Now I can perform and set up my equation. 240 kilopascals over 293 Kelvin is going to be equal to x over 321 Kelvin. I'm going to multiply both sides of the equation by 321 because I need to set and seclude x to one side of the equation. Now, I'm going to multiply 321 over 1 times 240 over 293 equals x. Multiplying that out, I get 262.9311 equals x. Now I just need to add my units. 262.9311 kilopascals is my unit. Make sure you convert to Kelvin. Question 3. A car tire has a pressure of 2.17747 atm at 32 degrees Celsius. The pressure of the tire goes down to 179.26419 kilopascals. What is the new temperature in Kelvin? I know I'm dealing with Gay-Lussac's law because I'm only dealing with temperature and pressure in the question and not volume. I can cross out volume because volume is constant. I'm left with P1 over T1 equals P2 over T2. Setting up my equation, I see that I have two different sets of units. I need to convert everything to the same units. So I'm going to convert everything to Kelvin and kilopascals. I need to convert 32 degrees Celsius to Kelvin by adding 32 plus 273 gets me 305 degrees Kelvin. Next, I need to multiply 2.17747 atm times 101.3 to get me 220.57 kilopascals. Now my equation is set up as 220.57 kilopascals over 305 degrees Kelvin is equal to 179.26419 kilopascals over x degrees Kelvin. I need to multiply both sides of the equation by 1 over 179.26419 kilopascals to get x secluded on one side of the equation. Multiplying that out, I get 247.833 equals x degrees Kelvin. Implementing my units, 247.88 degrees Kelvin is my answer. Thanks for watching.